Hello everyone, my name is Ji-Seok and I'm going to talk about high resolution soft resistive pressure sensor based on Elastomer Composite. Here are the whole contents of my presentation. First, at the introduction section, I will briefly introduce pressure sensors and freestanding membranes with through-hole. And I will explain experimental results with fabrication process and characteristics of sensors. Finally, I will summarize the presentation with future work. Electronic skin has attracted many attentions due to its possibilities to be applied to various applications. So many functions are applicable to electronic skin as shown in this picture, and pressure sensors can do a major role to realize electronic skin with pressure mapping for sensing, human-robot interaction, and health monitoring. Electronic skin with pressure sensors are actually qualified to be called skin because it can mimic the human skin with tactile receptors. This is a map of human tactile sense that shows the dynamic range and resolution of tactile receptors in each body part. Human body has tactile receptors with resolution of about 5 dpi, that is on the back of hand, to 100 dpi, that is on the lips. And moderate body motion shows the pressure range from 1 to 50 kilopascal. So, to mimic the human tactile sense or detect the human body motion, pressure sensors should have resolution up to 100 dpi and show pressure range of 1 to 50 kilopascal. There are 4 different main mechanisms that can realize pressure sensors. Resistive and capacitive pressure sensors literally detect the change of resistance and capacitance. Piezoelectric pressure sensors detect the generation of voltage, and piezo-phototronic pressure sensors emit the light when pressure is applied. Each pressure sensor has its pros and cons. Capacitive pressure sensors need complex readout elements because detecting change of capacitance is not that easy. Piezoelectric and phototronic sensors usually show poor stretchability because they need hard ceramic materials such as zinc oxide. Resistive pressure sensors have advantages of wide detection range and easy signal collection, but it is hard to fabricate high-resolution resistive pressure sensor arrays. There are a few papers that demonstrated high-resolution resistive pressure sensors. They use several structures with conductors and elastomer composite to obtain high resolution and softness of sensors. However, they need photolithography or CVD process that are expensive and time-consuming. Also, all these sensors show high power dissipation because resistance of sensors is relatively low even when pressure is not applied. Finally, no pressure mapping is conducted and whole sensor arrays act as just one pixel. To fabricate high-resolution pressure sensor arrays, I need a freestanding through-hole membranes. There are several methods for through-hole membranes, such as using capillary force, pressure, photoresist, and duetting phenomenon. Among these methods, using duetting phenomenon combining with spin cutting process has no limitation of materials and no needs of pressure control or expensive photolithography process. So this method is applied to fabricate through-hole membranes. This is the whole fabrication process of freestanding PDMS composite pressure sensor arrays. First, silicon vapor was etched with dry etching to obtain a mold and replicate those structures with PDMS. After peeling off PDMS pillar arrays from silicon mold, surface treatment was conducted to lower the adhesion force between pillar structures and PDMS through-hole membranes. After the treatment, PDMS prepolymer was spin coated and annealed to achieve micro-perforated structure. Finally, PDMS membrane was peeled off from the pillar structure and PDMS composite was injected into the whole arrays. This image shows the DRI etched silicon mold that shows hole size of 100 by 100 micrometer and hole depth of 300 micrometer. The pitch between each pixel is 200 micrometer and the resolution is about 125 dpi. After first replication process, as you can see at this SEM image, the pillar arrays of same scale with silicon mold were successfully obtained. After the second replication process, freestanding through-hole PDMS membrane was fabricated. The size of membrane is 5 by 5 cm in this image, and the size can be enlarged if 6 or 8 inch silicon mold were used. This membrane also shows the same structure with silicon mold. And at the right SEM image, you can check that 100 micrometer size through-hole arrays were successfully fabricated. The thickness of this membrane is same as the depth of hole arrays in the silicon mold. Finally, here is the PDMS composite pressure sensor arrays that PDMS composite was injected into the hole arrays that you saw at the previous slide. The filler is nickel nanoparticles with size of 100 nanometer and concentration of filler is 50 weight percent. As you can see at the right SEM image, each cell of pressure sensor is completely separated by the pure PDMS grid. So the possibilities of crosstalk between neighbor cells can be completely eliminated. This is the cyclic test result of the fabricated sensor arrays. Applied force is 100 gram force and the pressure is about 9 megapascal because of using sharp tip. At the early stages of cyclic test, the sensor showed good characteristics that the resistance changed from about 10 gigaohm to 10 kiloohm. However, when the cyclic test proceeded further, the resistance when the pressure is applied dramatically increased and the change of resistance was reduced. This phenomenon may be due to rearrangement of nickel particles in polymer matrix, and I have a result of improved cyclic characteristics with thinner sensor sheet. So I'm in the process of fabricating new silicon mold with shallower hole arrays to make a sensor sheet thinner than this. Finally, pressure mapping with 48 by 48 arrays was conducted. Flexible PCB with 250 micrometer pitch contact electrodes directly covered the up and down side of the sensor to make a contact with pressure sensor arrays. After the sensor arrays were connected to the commercialized board with flexible PCB, pressed O, A, and inverted 50 shapes successfully appeared on the computer. This is the summary of my today's presentation. High-resolution resistive pressure sensor arrays with PDMS composite were fabricated using the replication method. Pressure mapping of 48 by 48 sensor arrays was demonstrated with O, A, and 50 shapes. More optimization to solve the cyclic reliability issue will be conducted with thinner pressure sensor arrays. This is the end of my presentation. Thank you for your attention.